All right. Well, we'll get started right back at it. Talking about fuses. So, again, like I was talking about right before we left, fuses, two conductors where power comes in, power goes out. In between, you've got a thin wire usually, or some sort of conductor connecting the two. Now, because it's thin, it's susceptible to being overheated very easily. Because we always know that a byproduct, if I can do my words right today, a byproduct of electricity will always be traveling without electricity an amount of heat. And that heat will be relative to the amount of amperage and voltage going through that and the amount of resistance present in the wire. Now, a fuse is typically very, very low resistance, almost zero, or close as it can get to zero, because it wants power to pass through very, very easily. But if that power passes through so easily and yet it's still bringing in really high amperage and really high voltage, that's when the system will pop the fuse. That's when that fuse is going to disconnect, because that wire inside connecting those two conductors, that's going to be thermally overloaded. It's going to have where it's overheating typically, and that's going to allow for that wire to literally just burn apart. And if you were to take a fuse and you were to cut it in half after it popped, versus when you got a brand new fuse, you would see that disconnect. You would see burn marks on the wire inside. The easiest to see this on is on any kind of blade fuse for the control boards, like I was talking about before. Those, you'll actually pull them out of the control boards with a pair of needle nose pliers typically, or if just your fingers if it's easy enough to get to. And as soon as you pull it out, you can visually look at it, and in between where there's a little tiny connection, a little Z shape is what it looks like, where your fuse is, you'll see a little, basically, it looks like a little gray smoke mark, a little burn mark, basically. And that lets you know, okay, yeah, you got a pop fuse for sure. Always double check a fuse. You can check it with voltage to make sure if it's got power coming to it, it should read 0 volts across a fuse from one side to the other, because it's going to be, it's just going to let power pass right through it. It's not going to be a load of any kind. If you're testing with resistance, the only need to test with is continuity. Y'all have it on your meters. If you turn it to resistance, the ohm symbol, all right, and you press that select button 3 times, the red select button 3 times, it should bring up on the little visual display, they should have something that looks like a little speaker. And if you touch your leads together, it should beep. And that's called a continuity test. Now, it's a resistance test, but what it's doing is it's simplifying it. because I don't need to check the resistance of a fuse. I just need to check and make sure point A to point B, the start of the fuse and the end of the fuse, can I have power go through this? So with power disconnected, check on continuity. Don't, check the two sides of your fuse and just beep. Okay, good fuse. Bad fuse. You don't hear a beep, bad fuse. You hear a beep, good fuse. That's pretty much all there is to testing them. But you're going to replace a lot of fuses because this is one of the most common parts that, someone at the breaker trips in their house. Yeah, they usually know how to reset it. I'm not going to say everyone does, because definitely been to houses where it's just a trip breaker and had to go, flip a breaker on. I felt really bad for the people because, I go out to the unit and I'm like, yeah, everything's working as it should. Breaker probably tripped though because, yesterday was 105 degrees. Today is only 95, so it's able to handle it easily. And they're like, oh, that's all it was? I'm like, yeah, if you had tripped it, if you had flipped it yourselves, you guys probably would have been fine. So that's one of those things that's really common. But a fuse, people don't know where they're located. People don't know what size they are. People don't know how to install them. And so that is more of a safety for us as technicians. When it gets to the point where a fuse is going to pop in a system, it means that something majorly wrong is going on with that system, whether it's something is going wrong with the amount of amperage on the control side or something's wrong with the amperage on the load side. Our blower motor, our fan motor, condenser fan motor, our compressor, inducer draft motor, whatever it might be, those all have it where they can have fuses in place for them. So again, fuse, most common type of overload. Like I said, all we're testing for them is typically going to be, all right, continuity. Do I have the ability for voltage to pass through this or no? And that's as simple as it gets. If you don't, take it out, put a new one in. That's it. You're going to have, between, as far as actual repair parts on my truck, I always had contactors and capacitors, a lot of them. But I would say like repair parts, things that would be more for, hey, let's just, easy fix stuff. I had so many types of fuses. I had different brands, different sizes, different amperage ratings. I had minis, I had larges, I had blade fuses, I had every kind, because I was replacing fuses a lot. It's just what you do. You replace a lot of fuses. HVAC equipment requires extreme amounts of electricity. Because of that, because it's going to require that high load, because it's going to be costing so much to operate and repair, to avoid major repairs and everything like that, we include these kinds of safeties to make sure that the system's operating at least under somewhat ideal conditions. For a fuse, hey, it's not pulling too much amperage. Cool. But what about temperature? What about voltage? What about magnetism? That's when we're looking at these other types of overloads. So a line break and pilot duty overload, all right? These are two different ones that we're going to talk about. So the line break, easy enough. Breaks power to a motor, all right? Line, what it's talking about is line power, all right? We've got two things when we talk about power, especially with contactors. You're going to have a line side where power comes in from your power line. Okay, so it comes in, power line, goes to the breaker panel. From the breaker panel in the house, goes out to the outdoor unit. And then from the outdoor unit, goes right into the bottom of that contactor. That's your line power. The other side of that is your load power. All right, so the load power is going out to your loads, to your compressor, to your condenser fan motor, to your blower motor, whatever it might be. So the line break's whole idea is we're going to have it where we can control and make sure we're not going to have a compressor or a component overheating or turning on when it shouldn't. And how we're going to stop it from turning on. Oh, how can we do that? What would be the solution? Well, just put this switch, put this overload in series, all right, with the motor. Because if it's in series with the motor and it's open, well, then the motor is going to be treated as open and it's not going to turn on. And that's the whole idea behind a line break. With most of these overloads, that's the whole idea. A fuse, even, maybe it's not, it's not operating as a switch. It's literally just going to be disconnected. But that disconnection denies power to a system that would otherwise be operating under unsafe and harmful conditions to the system and its components. So pilot duties, we've got a couple of different styles. Current overload, a magnetic overload, or electronic solid state overload. All right. There we go. So this is not, okay, doesn't go into it as I'm used to the other slides that went a little more into the different styles of the pilot duty. Basically, current, we're sensing amperage. Okay, so it's going to be rated for a certain amount of amperage. When it senses that amperage, as far as a startup or anything like that, it will tell the system, it'll disconnect the system. It'll shut the motor down if it's drawing too much into it or anything like that. Magnetic overload is going to be if we have where a coil is causing magnetism too greatly. If we have it where it's drawing in so much power that that coil is creating a greater magnetic field than what is required, then we're going to be shutting the system down. Now, the cool thing about the magnetic overload is it's related to the current relay or the current overload. Because how would a coil generate a greater magnetic field without introducing more amperage, introducing more electricity at one time? That's going to increase the size of that field. As that field increases, disconnects the power and shuts down the system. And then electronic solid states, these are going to be more of your electronic sensor controls and control board controls that will actually choose when to turn on and off that system for various reasons, whether for a time delay relay or for a temperature delay, whatever it might be. Could be typically most common one for electronic solid state is for heat pumps. Compressors will stay off for a certain amount of time to allow for the system to balance its refrigerant back to where it needs to be, especially with that reversing valve, which you guys will learn about operating on a heat pump. So you'll see those used a lot for those. So troubleshooting, overloads, again, like I said, most are easy to troubleshoot, especially fuses. You're just checking for continuity. That's it. Most of these overloads, you're just checking to make sure, okay, power path load. That is the most basic, the most common way, the easiest way to boil down all of electrical, all right? And with an overload device, it's part of the path section. So we got our power, that's coming from our breaker panel, that's coming from our power plant, that's coming from our power line, all right? And it's got a long path from that breaker panel to our outdoor unit. It's going to be going through fuses, it's going to go through disconnects, it's going to go through overloads, all right? When we're troubleshooting, what we're going to look for is we're going to see, okay, well, my motor's not coming on. Well, first thing you want to check for, power. Is power getting to your motor? And if you don't have power at your motor, then you're going to start looking at that path from where the power started and where did it started and where along the way did it get lost, And so if you have power, and let's say you've got power at the breaker panel, and you've got power at your disconnect, and you've got power at your contactor, you got power coming out of your contactor, and then out on the other side of your contactor, you've got an overload device. You got power getting to your overload device, but then you check and you see power's not going from your overload device to your motor. That's where it stopped. Now, the difficult thing with an overload is to make sure that when you're troubleshooting it, you are looking at the problems. You're not just simply, oh, well, bad overload, replace the part. No, make sure that it's not having an error for a reason. Fuses will pop for a reason. Overloads will trip for a reason. There's either overheating. A system has got it where it's got too much amperage going into it. System's building too great a magnetism or something like that. Whatever it might be. These are the issues that we have to look at. So, because what's going to happen? I replaced that overload. Oh, seems to be working fine now. Well, the reason why it's working fine is because you just basically reset the overload by replacing it. And it runs, And it might run for 20 minutes. It might run for an hour. And then you might leave. And you might not have to come back until the next day. And then you've got to explain to that person, oh, well, yeah, I mean, I know it was an overload, but I didn't really have the time or didn't want to look into, why it tripped. I just wanted to replace the part. Yeah, they're going to love that. They're going to love hearing that from you. Now, what they want to hear is when you go out that first day, well, the overload seems to have tripped. This is usually caused by something going wrong with a motor. I'm going to check out the health of your motor and see if I can find anything that looks, suspicious. So I'm going to check capacitors. I'm going to see, okay, do I have anything for a capacitor that's messing up? Do I have one that's kind of low? I'm going to check my windings on everything. I'm going to check my amp draw on everything and make sure that it's not too high or too low. I'm going to check the resistance of my coils to make sure that I don't have an open or a short or excessive resistance for any reason. And then, that's when I'm really looking into all of my different components on the system, beyond just the overload and what it's protecting, but also everything else that it is, in series with, what it's functioning alongside with. That's what we have to look at. So we got a couple of different ones. The only difficult one, like it's saying right here, internal overload of a compressor. The tough one with that is typically those overloads will be set where it's going to be about 5 minutes. About could be more, could be less, than 5 minutes. But typically your your internal overload of a compressor is going to be either time or temperature is more common, sensitive. All right. So the problem you can have with these that's really easy to misdiagnose is people will say it's a bad compressor. And they'll say it's a bad compressor because they'll check across their windings and they'll read open. They'll read OL or they'll read infinity. And they know, oh, well, I've got an open winding. Then I obviously have a bad compressor, because typically that is the sign of a bad motor. If one winding is open, the motor's shot. It's done. That's all it takes. But an internal overload on a compressor is in series in the windings inside of that compressor. You cannot get to that component by itself. You have to let the compressor, the one thing you got to let it do is cool off. All right. This is the way that you can make it so that you can have a compressor actually that internal overload deactivating and closing contacts again and allowing that winding to be completed. So I've seen guys do this. I've had it before where they've gone and they diagnose bad compressor. Let's get a new one. They're under warranty. It's going to be no cost. It's going to be no problem. And they get out there, they take out the old compressor, put in the new one, the system starts right up, cool, they get out of there, and then they get called back to the office about a week later. Now, they're not getting called back to the customer's house because the system's working, it's fine, they replaced the compressor. Now, that compressor could have had some issues, it could have been, maybe having some problem or something like that. But I've seen a lot of guys do is they rush to a bad compressor diagnosis because it's a lot of money that you can make. If you replacing a compressor is a good chunk of change for a decent amount of work. Because they want that, or they're just thinking, I'd like to do a nice big job like that. That's when you're going to have, yeah, it's under warranty. We replaced it, got it done. Guy comes back to the office next week, and he's getting called into the boss's office because, hey, I'm being charged by the manufacturer for that compressor you put in. We have to pay for it. And you only budgeted for labor on your ticket. So what have I got to do? And the reason why the manufacturer's not going to pay for that compressor that you said had failed is because they got it back to their factory and they tested it and it hadn't failed. The system was working perfectly fine. You misdiagnosed, internal, overload. And that I've seen happen to guys. Now, depending on how often it happens, that's going to change the punishment level kind of thing. If a guy is continuously doing this, that's when a boss is going to start saying, well, guess what? The money we lost on it is coming out of your paycheck. If it's an honest mistake, if it's a first-time offense, kind of stuff like that, they're much more understandable. Okay, yep, you messed up, whatever, misdiagnosed. Just in the future, pay attention to this, this, and this. You know, they might talk to you for a while about compressor diagnosing and understanding how to do that kind of stuff. But you don't want to be the guy that misdiagnoses an internal failure as far as an internal overload when it, you know, and you think it's an open winding. Because I've thought that before. I've had it before where I, you know, when I first started out, I thought I had a bad compressor on one of my first like big like diagnostic calls, and I called my buddies up. I was like, man, dude, the thing's like, I've got it open. I don't know what's going on. He's like, all right, where's the open between start and com? And okay, well, give it a minute. How long has it been since that thing's been off? Oh, I don't know, 30 seconds. Dude, no, give it like 5 minutes at least. And that's all he told me. You know, he's like, hey, give it 5 minutes. I gave it 5 minutes. All of a sudden, oh, there's not an open winding anymore. Wonder how that happened. Did the motor magically repair itself? No, it overheated and then it cooled itself off. But the other thing he told me, he's like, hey, you've got a problem with overheating. Start looking for issues with overheating. See for, you know, check things like airflow. If you've got a blower motor and it's not getting enough airflow, it's going to overheat. It's going to have an open winding if it's got an internal overload, you know, system on it. But for the compressors, because they're going to be, you know, you're not going to be able to get to those overloads or anything like that. They're sealed inside that hermetic compressor. That's when you actually have it where it's not just going to be, you know, diagnosing, yes, it's a bad compressor, no, it's a good one. You're looking at those internal overloads to make sure, okay, yes, I've got it where it's functioning properly, the internal overload's doing its job, but why is it overloading, you know? So you look at, like I said, if for an outdoor compressor, you're going to look at outdoor coils, airflow again, make sure that the coil's not gunked up. You guys, honestly, if you want to, when you're out walking around town or anything like that, if you feel like being a really weird dude, trust me, I do this every now and then because I'm crazy. I look at air conditioners. When I'm walking next to houses, I just casually look over. I'm not like going up next to them or anything like that and inspecting them, but like I'm walking my dog, I'm out, I'm looking at condenser units. And you can visually see from a distance some units how dirty they've gotten. And from others, you can see how new they are, you know? Brand new units at someone's place, they're going to look like shiny aluminum, beautiful, gorgeous units. It's pretty wonderful. I love a good clean unit. Is just something to behold. And the reason is because a good clean unit is getting airflow. It's getting heat transfer. It's getting energy efficiency. It's maintaining the level of cooling that it was designed to do. So that's a really common thing to cause an overload or an overheating on a compressor in the summertime, especially because it's running, it's got that air conditioning going, and it's pumping that refrigerant around and around and around. The only thing cooling that compressor off is literally the refrigerant going through it, pretty much. That's it. Airflow and the refrigerant. The airflow really doesn't help too much because the airflow, honestly, is increasing in heat as it goes across that condenser coil and surrounds that compressor. And then that compressor's got it where now it's got all that heat sitting right on top of it, and all that's cooling it off is the refrigerant that it's compressing that's going through it. You've got that low pressure, low temperature vapor coming in from the evaporator. That's cooling that compressor off, but just so slightly. So another thing I might look for a restriction in my suction line. I might look for a lack of refrigerant in my system. These are other things that are going to cause that overheating that we see in our compressors for outdoor units. Well, not for outdoor units, but of course for outdoor units. For our compressors in a in an air conditioning system or anything like that, especially for hermetically sealed residential systems. That's what we're going to be seeing. So. All right, magnetic starters. These are really interesting. I'm going to, because we don't have any at the school or anything like that, I'm definitely going to send out a video for you guys to watch. That's going to show you how magnetic starter works and everything like that. It's very similar to a contactor, but basically it's going to be starting system for larger units. That's what you're going to see a magnetic starter used for a lot of times. So it will have, it's not just going to be a contactor though, it's also going to have parts of it that will be like overload device. So basically a contactor and an overload device made a baby, and that is a magnetic starter or a motor start. That's what you're going to be seeing a lot of times for those. But I'll send out a video when I send out the ones from today as well, to show you guys magnetic starters as far as different things on them, how to test them, what they look like is the main thing, because this has got no pictures of it. Your book has got some, I think, but oh yeah, these old school ones. That is ancient technology in that slide right there. That is not used too often. That looks honestly like a fuse.
Excuse me, young fella. You mind going back right quick for a couple seconds?
Yep, I got you.
I just gotta get that last part.
Yeah.
The energizer's coil. Okay, that's it.
Yep.
Hey, Mr. Williams.
Yes, sir.
So all of these are going to be on YouTube?
Yep, I'm going to put them all up on YouTube.
Okay.
Yep.
Just making sure. Thanks.
Yeah. So you can review them. And then I need to double check. I should have it where I've put, if I haven't already, I'll make sure to put the slides will be on Canvas as well.
All right.
You can download and look at them there as well. That's the whole plan with that. All right. So okay, there we go. Yeah. Okay. I know how slides work. So we've got a couple different styles of them, I guess. This is the bimetal relay. And this is where it's going to be operating pretty much. Is it the bimetal? Honestly, I don't know. I think that is old. Some old technology. But the whole idea, again, with these relays or these starters is that we are operating and controlling based on some outside information or external factor for our motor. So bimetal relay, it's going to be dealing with heat. All right, you've got it where bimetal is always going to be reacting to heat. It's going to bend and warp its shape. Thermal, again, heat. And the molten alloy relay is going to be based on heat as well. Basically, you're going to have it where this molten alloy is going to allow for power to pass through and everything with this link of material. So we've got a couple different styles of them, but again, I'll send that video out later for y'all. So troubleshooting a magnetic starter, basically you're going to be making sure you're looking at contacts, coil, overloads, and mechanical linkage. So the same parts we've already looked at for contactors and for relays, we're also going to be looking at for magnetic starters. But with a magnetic starter, remember, it's also going to be having an overload device. That overload device is something else you have to troubleshoot. Is it opening on high temperature when it needs to, or is it opening up, if it opens up on high temperature and the system's not running at really high amperage and it's wintertime, definitely an issue, but if it's running at a really hard system on a hot day, then yes, I would not be surprised if we have an overload activating as it normally would. So now, push button stations, these are very old school. This is industrial nowadays. It's about the only spot you're going to see a push button system used. It is the most basic. All right, you've got it where it's going to be switches, which is either closed or open. That's it. All right, and depending on what the job is, it will do different things. So for instance, with this switch that they've got here, it's got 3 things that it can do. It can either go forward, reverse, or stop. All right, so this is going to be your disconnect or off switch, basically part of it. And then you can control with this one, you've got it where it can actually control the rotation of whatever it's controlling. Either it's going to go forward or it's going to go in reverse. So this is used a lot of times for large industrial stations and everything like that. They'll have a single switchboard panel, like Homer Simpson style. I'm not even joking. And it's literally you just pressing everything, turning dials, and operating the HVAC system for an industrial plant or something like that. Now, nowadays, they're getting away from this. They're having it where it's much more the DDC, direct digital controls. Everything is being fed through digital switches and signals and everything like that. But a lot of old school stuff, and there's still some old school that's even gotten the DDC with it that still is like DDC and push button. So you'll have them combined together. And it just depends on what's the need, what's the requirement. The big thing with it, though, is this is not automated. This is going to be manually controlled. So you have it where, it's manually controlled, someone's going to be there to control it. So it's going to be some sort of industrial system more often than not, like I said, because if it's comfort heating and cooling, no way do we need to have an HVAC tech at someone's house all day, every day, just operating their air conditioner. That's kind of creepy and a little weird and a waste of money and time. We have those automatically. But for industrial processing, refrigeration, like tissue sampling, ice making on an industrial scale, even places like paper mills and stuff like that have heating and cooling needs. Philip Morris, they're going to be all having it where these push button systems are used a lot of times because it's easier, it's more controllable, and you can have it where one person comes in, next person comes in, you keep them on a shift, you keep the thing keeps running. But if something needs to stop for an emergency reason, if something needs to shut down immediately, if something needs to shut off for maintenance, it's going to be regularly scheduled. It's going to be easy to control. It's not going to be, oh, we got to disconnect power. Where's the breaker at? No, it's labeled right on the board. We've got compressor 35 off. Here's compressor 22, press the button, off. All right, fan, we need to have that go in the reverse direction. All right, let's kick the reverse in, whatever it might be. So these switches and these controls are going to be used a lot like any other switch or control we'd have for, anything, just like a wall switch. We're going to test them with resistance. We're going to test them with voltage and make sure that power is passing through there as it should. So that's literally all there is to a push button station, but they're used a lot of times for these more commercial applications and everything like that, especially industrial applications. All right, so keep in mind, again, relays, contactors, magnetic starters, especially relays and contactors, those right there, same thing. Only difference is contactors handle a much higher load, relays handle a much smaller load. All right, so smaller motors, relays. Big motors, contactors. By big motor, I just mean even a residential compressor. That's going to need a contactor that is not going to run off of a relay. Overloads are protective devices that are making sure that either temperature or amperage or whatever factor we're looking at is not exceeding safety as far as operation of the motor. And then the magnetic starter is going to be like a contactor with an overload. Those two basically had a baby together. I don't know. No. Okay. That was weird. So magnetic starter, again, it's going to be a contactor and a overload, basically comboed together. And I'll send out a video explaining a little bit more about those. That way you guys can get a little more visual look at what a magnetic relay looks like and everything like that. But other than that, we are done with chapter 10 for today. I thank you for your time, and I will see y'all again on Wednesday.
So we'll be getting that homework Wednesday?
Yeah, I'll be handing out the homework. And I'll make sure to send that out and everything by then.
Okay, if you don't, it's not that big of a deal. You can.
Yeah, you guys can get away with no homework, right?
Yep.
Yeah.
Yeah.
Yeah. No, I'll make sure to get all that info out to y'all and give you the dates and everything for it.
All right, thanks, man.
All right.
All right. Thanks, gents.